Okay, so my part will be a little bit more technical because I was thinking to introduce some of the work I have done when I was a PhD with Dr. Duan, and this is something that moved the EQdyna from dynamic rupture modeling towards a full range of faulting behavior simulation and being suitable for earthquake cycle modeling. So I will give you some of the details of how I did it when I was working on this project. So yeah, let me go to the full screen. So Dr. Duan and Duanyu has given a great overview of the tools that we have developed. And one of our goals is to, of course, to study the earthquake source mechanism. And back then, Dr. Duan has already developed this EQdyna 3D code for 3D dynamic rupture simulation. And of course, we want this code to be more powerful to become the ideal tool to simulate the earthquake cycle, and also allow the simulation to be spontaneous, which means we don't need other prescribed conditions to push the model to move. We want it to move spontaneously according to some initial conditions. And so in order to do that, one of the key component to change in Dr. Dan's previous code is the friction law. So in order to simulate dynamic rupture, we actually only need the slip weakening friction law, which is kind of a descriptive law of how the friction will behave when the faults start to slip. And that's enough for dynamic rupture, but it will not spontaneously move to the next earthquake if you are trying to put it in an earthquake cycle modeling context. So rate state friction, rate and state dependent friction actually has been proposed from physical experiments to kind of take place of this role, and also this law is able to being able to capture the slow faulting behavior even between the earthquakes. So using rate and state friction, we can actually do earthquake cycle modeling. So that's one of the key tasks that I was working on when I was a PhD student. So this is some of the steps that we want, some of the components when we are trying to develop this earthquake cycle modeling code. So the idea is, of course, there are many other different kinds of earthquake cycle modeling codes, and from different perspectives using different levels of assumptions. And our idea is to push it to the fully elastodynamic level, which means the earthquake rupture part, we want to simulate it using the complete equation of motions. And also between the earthquakes, we try to simulate the quasi-static process as accurate as possible. And to do that, of course, we have one important step to convert, which is to convert the dynamic rupture as the EQdyna code into a quasi-static simulation code, which I believe Qingjun will talk about in the next section, which is using the dynamic relaxation technique to do the job. And the last part, the third part is what I'm trying to talk about, which is to implement this rate and state dependent friction law into the code. So basically, an essential form of this law is given here. So it's basically trying to describe the friction coefficient dependent on the slipping rate of the fault. And also there will be a state variable theta that describes the state of the interface. So there are some physical explanation of this parameter, but it's still actually not very clear what it actually means. But still, this works very well in describing how the fault behaves. So this friction law actually is now kind of widely used for earthquake simulation and earthquake cycle modeling. And also the parameter theta also evolves according to the aging law, or the so-called aging law, or there's another law which is called the slip law, which also can describe the evolution of the state variable. So if you look at the literature, there are a number of different kinds of forms of mathematical forms of this rate and state friction laws. Well, there are different kinds of them, and they could be implemented in different ways, but they share the same properties, which is the logarithmic dependence of the friction on velocity, and also the logarithmic dependence of the friction on a state variable. So this is the essential form of it. So today what I'm going to talk about is how we implement this friction law into our EQdyna code. So it's actually a little bit tricky, and I need to go back to what Dr. Duan has shown previously, the traction as split node scheme, because for the EQdyna actually simulates the whole, the evolution of the whole media, including the motion of the off-fault material and also the slip on the fault. So basically including almost everything. But in terms of rate and state friction, is actually, it only occurs on the fault because we are talking about the friction only. So we will be looking at those split nodes, which describes the interacting fault. So we need to go back to, when I was working on it, I need to go back to Professor Steve Day's 2005 paper. And so basically in his paper, he has this formula to describe how the nodes should evolve, or say, let's say how the velocities and displacements of this node should be updated as the simulation marches forward. But the idea is quite simple, which is you can see the new velocity is the old velocity plus increment, and the increment is basically the force divided by mass, so it's the acceleration. So it's actually quite simple. The updating scheme is quite simple, and this is the displacement updating equation. And what's important in his paper is to propose a traction that's defined in this way. And this traction is actually used to calculate the maximum friction that's allowed between the nodes. And this is the maximum value to log the fault, because you can see the logic is to say, okay, if there's some slip between the nodes, and the maximum traction that's allowed between the nodes is the friction that puts the sliding to a complete stop. And then you cannot have even larger traction, because a greater traction will introduce a reverse slip, which is unrealistic, non-physical, because friction is a passive force. You cannot use friction to push something to give momentum to some material. So this is the logic of defining this parameter. And in his work, this parameter is a cap of the friction, the maximum value of the friction, and then he implement the slip weakening law by scaling down this parameter accordingly. So from the static friction down to the dynamic friction. So when the friction goes down from the maximum value to a lower level, then you will have you will still have a difference between the elastic force and the friction, which creates the which yields the acceleration, and then the slip will start, the split nodes will start to slip relative to each other, and then you have this spontaneous dynamic rupture that occurs. So this is the logic, this is the background of the implementation of the friction law in EQdyna. And what I did basically is to modify this scheme to in order to incorporate the rate and state friction, which is, like Dr. Duan has mentioned, is a bit tricky because now friction depends on the slip rates, and we need to find out how to relay them accordingly. So, well, at the beginning, I was trying to define some new framework to implement this friction law, but later on, I realized actually I should do this under Professor Steve Day's scheme. So what I did is basically to go from his velocity updating scheme to obtain this slip rate updating scheme. So I will obtain this equation, and I also use the same definition of the maximum friction as in his paper. And what I do is to like here, I actually substitute this whole thing into the slip rate updating scheme. So actually this equation can be simplified and becomes a very simple equation like this. We have this new slip rate comes from the maximum traction minus a actual traction. And this actual traction, if we go back to slip weakening friction law, this is what we were talking about, that it will change, it will evolve from static friction to dynamic friction. But now for the rate and state friction, we need to replace this by the rate and state dependent friction law. And this and the replacement is a little bit tricky because you can't just use a very simple, like say, one step forward updating scheme to do that, because that will be unstable. Actually, some of the quite a lot of paper has talked about this, but back then when I was just started this project, it took me a while to to understand why. It's all about numerical stability. So basically, we will need at least backward Euler or central differencing scheme that's actually implicit. That means the traction should be related to the new slip rate, and also as well as the new slip rate as well as the old slip rate. So if I substitute this equation into the top one here, then we'll see there's a new slip rate on the right-hand side that should be moved to the left-hand side. And this equation should be solved iteratively. So Newton's method is good enough to solve it, but you can see the new slip rate here is actually a parameter of the this friction coefficient. So this equation should be solved iteratively. And when I get to this point, this is the last step where I can successfully implement this into EQdyna. So combining this updating scheme for the slip rate as well as the evolution law for the state parameter, state variable, I can do rate and state friction simulation for earthquake rupture. So this is my paper with Dr. Duan in 2018, trying to compare the effect of different friction laws like slip weakening law, rate state friction law with the aging evolution law, and rate state friction with the slip evolution law, as well as the flash heating raised friction loss. So a comparison of multiple different friction loss for earthquake cycle modeling. Sorry, earthquake modeling, rupture modeling. So this is some of the details of the paper. I guess I will just skip most of it. Because if you are interested, you can contact me or refer to my paper. Is all about how different kinds of friction will control the behavior of the process of the faulting, and also when there's a bump on the fault, which is kind of irregular geometry of the fault surface. So I have some of the results here. Yes, I'll just skip here. Yes, so I basically quickly go through the details of implementing raised friction, and this is kind of the foundation of, like I said before, a foundation for moving forward towards earthquake cycle simulation, which I believe Qingjun will talk about later. Yeah, so I guess I will stop here and see if there are any questions.